I rewrite this first one as 4 minus 3x squared to the 1/2 power, we've done that for sure. So 4 minus 3x squared to the 1/2 power. What's different about this that we haven't seen before? Right, so rather than just one term being raised to the 1/2 power, we have like a function within this. So what you're going to do to take the derivative is kind of look at it holistically at first. So holistically, this is something being raised to the 1/2 power. So we're still going to follow our power rule. So we're going to bring that 1/2 out in front, leave the base completely untouched, and then raised to the negative 1/2 power. So that would just be the application of the power rule right there. The chain rule comes in because you then have to multiply this by the derivative of what's inside here. So the derivative of the function in the parentheses, which would just be what? Negative 6x. So then we would clean this up. This whole piece is going to the denominator. So we have negative 6x up top over 2 parentheses. Well, we don't need parentheses because I'll turn it into a root at the same time. Root 4 minus 3x squared. And then our 6 and our 2 will reduce to negative 3x over root 4 minus 3x squared. Okie doke. In the next one, now you could do this one with the quotient rule and not have to use the chain rule, but I'm going to rewrite it first as 4 minus 5t minus t squared to the negative first power, and I'm going to make myself use the chain rule. And again, you'll gravitate towards whatever works better for you. There's no right or wrong way. Like if you really like the quotient rule, you can do that. But I would probably do the chain rule here. So I'd bring my negative 1 out in front. This is all raised to now the negative second power. But since the base of this is its own kind of function, we have to multiply that power rule application times the derivative of what's inside, which will be negative 2t minus 5. And then we'll just clean that up. So this piece is moving to my denominator. That'll be 4 minus 5t minus t squared in the denominator. And in my numerator is this negative 1 times negative 2t minus 5, which will just be 2t plus 5. Any questions there? Okay. In this one, you would almost definitely just jump right into the quotient rule. If you bring this up top, it's just going to be the product rule. So again, you'll start to gravitate and just go with your method. I'm going to start this one using the quotient rule. The only thing I might do is rewrite this to the 1/2 power just so I can visualize that power rule when I get down there. So bottom times the derivative of the top is nice and easy, 1, minus the top. The derivative of the bottom here is going to be where your chain rule comes in. Because on the forefront, it's power rule. You bring your 1/2 out in front, x to the 4th plus 4 to the negative 1/2 power. But then you have to multiply that by the derivative of what's inside, which will be what? Stephanie? 4x cubed. And then so constantly you're detouring So you have to constantly center yourself. Where was I in this process? Bottom times derivative of the top minus top times derivative of the bottom. All over. Now the bottom squared here is just going to be what? X to the fourth plus 4, correct. So the cleanup. Oof. All right. I'll bring this one back to a radical. So that's going to be the square root of x to the fourth plus 4. On this one, this has to move within its own denominator, not to this denominator. It's going to create a complex fraction here. So you've got up top, you're going to have an x times a 1 times a 4x cubed, which is going to be 4x to the fourth. On the bottom, you're going to have 2 root x to the fourth plus 4. All over x to the fourth plus 4. Now your 4 and 2 can cancel to make that just a 2. And then we have to clear our complex fraction by multiplying by this denominator, root x to the fourth plus 4 on the top, root x to the fourth plus 4 on the bottom. So when I distribute that up top, I'm going to initially get x to the fourth plus 4. When I distribute it to the second term, that's just going to clear that denominator, so you're going to have minus 2x to the fourth over the x to the fourth plus 4 that was there times the new root x to the fourth plus 4. And then I can just combine like terms in my numerator. So x to the fourth minus 2x to the fourth is negative x to the fourth plus 4. And I'm there. Couple things that I want to mention in doing that I know just thinking back is a common mistake. This x to the fourth plus 4 has to have parentheses around it. If it doesn't, it's not right. If it doesn't, it's going to look like only the 4 gets multiplied by the radical, when in reality, this x to the fourth plus 4 is an entire factor in and of itself. So that's issue number 1. Number 2, I think it's probably looking tempting to a lot of you, this x to the fourth, negative x to the fourth plus 4 over the x to the fourth plus 4, but that cannot be canceled because that's a different thing. If the negative sign was out in front of a set of parentheses, then we could do that. But this negative is just on the x to the fourth term because of the combining that happened. So we are done here, unless perhaps they rationalize, but in calculus, rationalization is less of a thing. Okay? Any questions on that? Now, if we had time, we could redo that exact same problem from the product rule standpoint. We're not going to do that, but it would have led us to the same answer. You might think, well, maybe that's easier. You really just don't know sometimes until you just start doing it. I can't tell in advance if the product rule would have been easier, or maybe more complicated, or maybe just the same. But you just go with one. If you do have time and you want to like check things, you could try it a different way. Any questions? Okay. On this next one, you could do a couple things, but I'm going to choose to see this one first as just something cubed. So I'm going to just start with the power rule based on the fact that this is something cubed. So g prime of x is going to be bringing the 3 out in front. And then that quotient is now only being squared. But then, of course, I have to multiply it by the derivative of what's inside. And that's where we're going to have to do a quotient rule. So the derivative of what's inside there is the bottom, 2x plus 3, times the derivative of the top will just be 6x minus the top, 3x squared minus 2, times the derivative of the bottom, just 2, all over bottom squared. Okay? So, when you're squaring a fraction, so going back here, you're squaring the numerator and you're squaring the denominator. So when I rewrite this, I'm going to do 3x squared minus 2 squared over 2x plus 3 squared. Times, and then this denominator is still going to stay 2x plus 3 squared. Up top over here, maybe I want to do some preliminary work up here. I would distribute my 6x, so I'd get 12x squared plus 18x. Distribute my negative 2, I'd get minus 6x squared plus 4. That's me distributing the negative 2. So that will clean up and will be 6x squared plus 18x plus 4. Now, is that factorable? I can definitely take a 2 out. 3x squared plus 9x plus 2. And then I don't think I can do it any further than that. On the numerator, I'm talking. Give me 1 second, Josh. So, here's where I am. Up top, I've got a 3 and a 2 for monomials, so that's 6. Then I've got this 3x squared minus 2 squared. And I've got this trinomial 3x squared plus 9x plus 2. All over what? Good. 2x plus 3 to the 4th. Josh.
If you didn't want to do this, this is absolutely painful, could you just do the quotient rule and cube that? Is that how you go about it?
No. What you could do is you could cube this. It's going to be painful no matter which way you do it. You could cube this to start, meaning you could do 3x squared minus 2 cubed over 2x plus 3 cubed and do the quotient rule right off the bat. But that quotient rule, when you do the bottom, you're fine, times the derivative of the top is going to require the chain. Do you follow? If I take the derivative of the top, I'm going to have to bring the 3 out in front, drop to a 2, then multiply it by 6x. Does that make sense? So it's not going to be, I mean, it might, like I said, it's a lot of times it's going to be 6 of one, half a dozen of the other. Meaning, do you know that phrase? Raise your hand if you've heard that phrase before. 6 of one, half a dozen of the other. Oh boy. Means it's going to be the same either way you look at it. Yeah.
How would you ask this in a multiple choice? If they went on a test, it would take us like 20 minutes. And we had like 5 minutes to take a test.
I know. So the number of problems goes down. I know. So you could do that, Josh, and organize it that way, absolutely. But either way, it's going to be chain rules within a quotient or vice versa, quotient within the chain. Yes.
Could you avoid it altogether by just doing, you put the 3 out, like for the top, you put the 3 out in front, and then you have 3x squared minus 2 squared, and then just write it out again, 3x squared minus 2.
Like actually cube this out and actually cube this out and then do quotient.
Or no, what you said where you bring the 3 out in front and make that squared?
Right here.
Yeah, basically. Do that.
But that's me already, I've already started the derivative. That's not a way of rewriting the original to do it a different method. By doing that power rule, I've already started the derivative process.
I think he's trying to say do the derivative of the top and then the derivative of 3x squared minus 2 to the third, and then the derivative of the 2x plus 3 to the third, and then do the quotient. Is that
So if we change both forms.
I don't think that would work. That's not how you take the derivative of a quotient. You don't just take the derivative of the top and take the derivative of the bottom. You have to do the quotient rule, which is that whole bottom derivative top process. All right.
I'm trying to avoid this whole thing.
It's not going to work. All right. Examine the graphs of each of these alongside the graphs of their derivatives and discuss what we notice. Oh, this is fun. This is just a light bulb moment kind of activity. So I'm going to, you don't have to do anything, just watch and appreciate. Okay, so I'm going to graph the original. X divided by the square root of x to the fourth plus 4. They want us to examine that graph alongside the graph of its derivative, which is down here. So negative x to the fourth plus 4 over. I need a big set of brackets around my denominator here. So there it is. And then I need my own set of brackets around x to the fourth plus 4 and square root of x to the fourth plus 4, and then close the big denominator. So there's my original function, which is not, I'm going to have to change the window to see what's going on there. Okay, yeah, we're really way in here. So I'm going to go, I'll go negative 10 to 10, but I'm going to go like negative 2 to 2. What do you notice about the slope of that? Negative, right? 0. Then it's positive, so see how the derivative went above the x-axis? So we have a negative slope, very slightly negative though, so that's why this derivative was underneath the x-axis, but not by much. Then it got more and more negative, which is why this is coming down a little bit. And then it had a slope of 0 right here, which is why this has a root on the derivative. And then the slope of the original starts being positive, this whole stretch, which is why this is in the positives. And it's positive until here, where it's a slope of 0 again. So if you look at your derivative graph, it has a root. And then the slope is negative. More negative first, then it eventually is still negative, but not as much so. So we're underneath the x-axis by less and less each time. Good? So comparing the two functions. Good, that's our discussion. Okay, flip to the back. Chain rule is still going to apply here with the trig stuff. So on this first one, there's first and foremost a very important thing you have to know. This is different than this. Okay? In the case of secant squared x, that's equivalent to taking the secant of x and squaring it. This is just squaring the piece that you're taking the secant up. So order of operation wise here, whatever x is you would square first, and then you would take the secant of it. Written in either one of this way, you take the secant of x first and then square that answer. So when you're taking the derivative of this way, and they don't have the parentheses there, but I'm putting them in there so that you can see how this is organized a little bit more clearly. And from the outside looking in, so looking at this thing holistically, we're taking the secant of something. So the derivative of secant is what? Secant tan. So the derivative of this secant x squared is going to be secant x squared tangent x squared. And that's just taking the derivative of the secant function. But there's a chain rule here because we have to multiply it by the derivative of what's inside, which is, what's the derivative of x squared? 2x. So this ends up being, and usually they'll just put the monomial out in front, 2x secant of x squared, tangent of x squared. Because this has its own derivative. So here's the thing. Up until this point, let me see if I can grab. I mean, we could argue that we were doing the chain rule, even with a simple example like, when in doubt, do it. So like even when we started day one and we just had x to the fifth and we did the power rule. If you did the chain rule, which would be the derivative of that is 5x to the fourth times the derivative of what's inside. What's inside? What's the derivative of that? 1. So you could technically still do it, but the derivative of what's inside would just be 1 and it wouldn't matter. So we haven't mentioned it because up until this point the derivative of what's inside has been 1 and we haven't had to worry about it. I mean, you could argue if this was a constant, not that you would ever do this because you know this derivative is just 0, but you could argue that you would bring your 5 out in front times 3 to the 4th power times the derivative of what's inside is just 0, and so that trumps the whole thing and makes it 0 as well. So you could argue that we've been doing it all along without really realizing it. So when in doubt, assume it applies. Does that make sense? You'll get a feel for it the more you see this. On this one, similarly, we're taking the cosine from holistically, this is the cosine of something. So the derivative of cosine is negative sine of, you don't change anything else the first time through. The derivative of cosine is negative sine and leave everything else the same. But then we have to multiply that by the derivative of what's inside. Here's what's inside. So what's the derivative of 1 minus 2x squared? A chain rule within the chain rule. Yes? So if you have to do the derivative of this piece, you want to look at this from the outside looking in just here, it would be a power rule. Bring your 2 out in front, times the 1 minus 2x to the first power, then times the derivative of what's inside of that. What's the derivative of this most inner part? Negative 2 times negative 2. So, when this is all said and done on the second piece, it's going to be negative, well, I'm going to be distributing a negative 4, or I can just leave it as negative 4, 1 minus 2x. So again, typically you're going to bring your monomials and such out in front. So the negative 4 times the negative that's out in front will just be a 4. This 1 minus 2x goes out, would probably go out in front. 1 minus 2x, and then it's the sine of 1 minus 2x squared. This 1 minus 2x over here, just you're not taking the sine of that. You're only taking the sine of this. Anything else that comes thereafter is being multiplied out in front. If you want to distribute that 4, I suppose you could. But if you do distribute that 4, that whole binomial still has to be in parentheses. Okay. This is nice because it doesn't appear to have the chain rule. What's that? I don't think it does. No, because it's just v. And okay, so we're just going to do a quotient. Yes? Is that your preference? So g prime of v, bottom times derivative of the top minus the top. What's the derivative of cosecant? Negative cosecant cotangent all over bottom squared. So negative cosecant v sine v plus yuck. Cosine V, cosecant V, cotangent V. There's going to be a decent amount of playing around with this from an identity standpoint to try to get things to cancel. Because cosecant is what? 1 over sine. So guess what? This is all going to just become -1. Plus, this is cosine V. Cosecant is 1 over sine V. So this is, cosine over sine is the same as cotangent times another cotangent is a cotangent squared over cosecant V. And you could put your square on the inner part of the cosecant if you want. Yep. Yep. Is -1 plus cotangent squared an identity? It must be. Let me remind myself of the sine squared plus cosine squared is 1. And to get a cotangent, you would divide everything by sine squared. Sine squared, sine squared, sine squared. So one of our other identities is 1 plus cotangent squared equals cosecant squared. We don't have that. We have cotangent squared -1. So we actually really can't do much more with it than this. Okay, but yeah, so you're either going to manipulate later or earlier. So if you wanted to in the beginning, what they're saying is we could have, and again, you'll come up with your preferences, we could have changed the cosecant to 1 over sine. We could keep cosine V, change flip. And did you guys just use the product rule then with cosines and sines? Okay. Did it get you to the same answer, Liam?
No.
Totally different? Somewhat similar? So what is your final answer? If you did this and did the product rule, what did you get?
Cosine squared V minus sine squared V. It looks like if you just turn your cosecant squared V into a 1 over sine squared.
And keep change flip kind of thing?
Yeah, and then do the same for cotangent squared, you might end up with the same.
So if this is what he got and this is what we got, they must be equal. And so this is where just kind of playing around with it and almost doing an identity problem just to make sure you've got the right answer would come in. Okay? That can get tricky, obviously, because you don't know if you're looking at multiple choice, is it going to do it this way and give you an answer in that ballpark, or is it going to do it the product rule way? So you have to be pretty fluent with just not sighing and complaining when it comes up. You just have to start manipulating and working towards a different version. And maybe you want to look at your answers first, take a peek at them, and see if that gives you any insight as to which method you should use. But it can get tricky. All right, this one is, I want you to first look at the arrangement of this. Because this is not a product rule situation, okay? And let me show you, don't write this down. This is what I don't want you to think this is. This is not, this would use a product rule. The sine x times the tangent of pi x. But this is actually taking the sine of this. Do we follow? Okay, so make sure we're seeing that correctly first and foremost. So the derivative, from the outside looking in, this is just a sine function. So the derivative of sine is cosine. Cosine of whatever, just leave it. Then you have to multiply that by the derivative of what's inside. So what's inside is a tangent function. What's the derivative of tangent? Secant squared of pi x. But then, again, there's a derivative of what's inside of that. What's the derivative of pi x? Pi. So I don't know in what order they would put this, other than the fact that pi is definitely out in front, but you could just bring that out in front and leave everything else the same. Pi times the cosine of tangent pi x times secant squared of pi x. All right, just a little bit messier. Conceptually not hard, algebraically very, very messy. I don't know what you prefer, but